Okay. Now we will officially get started. Thank you everyone for joining us today. This is a joint workshop presented by Amazon Braket and A-Quantum. This is a two-day event. Today, day one, you will learn about Amazon Braket, and tomorrow, day two, we will learn about QuantumPath, which is A-Quantum's software as a solution that runs on Amazon Braket. But before we get to the workshop, some housekeeping items. Attendees, please do not unmute yourself. This is a large event, so we do want to avoid any issues from the background noises. If you have any questions during the workshop, please feel free to use the chat button on the right side of your WebEx screen. Any questions that you have or any issues you face, there are moderators in the session to help you, so they will take care of any issues that you may have. Throughout the presentation, if at any time you have questions, please do not hesitate to type it in the chat button. We will try our best to get it answered, but if we cannot, we will also make sure that we get to the question after the event. Another important notification, this event is being recorded, so keep that in mind. Before we get to the agenda, I wanted to briefly introduce A-Quantum as one of our partners in AWS Partner Network. A-Quantum has been working with us very closely in the last 1 year to build their software, and tomorrow you'll see how awesome that software is on top of Amazon Braket, and allows you to do quantum computing by lowering the barrier to entry. Right, so with that, I'd like to jump to the agenda. Like I said before, today's day one. We'll do the introductions for Amazon Braket. There's some hands-on part. We highly encourage that you actually get hands-on with Amazon Braket, and that will also prepare you for tomorrow, where we also will do some hands-on activities with QuantumPath. So a closer look at the agenda for today. We'll do some introductions, and then one of my co-workers will take it over and show you how to do some introductory workloads on Amazon Braket. But before we get that, introductions for your speaker. My name is Nihit Pokhrel. I'm a Partner Solutions Architect in the High Performance Computing team at Amazon Web Services, and I work with ISV, independent software vendors that build product on Amazon Web Services, particularly pertaining to quantum computing and high performance computing. Pepe, you're next.
Hi to everybody. Sorry because I cannot unmute myself. My name is Jose Lucevia, but I prefer that you call me Pepe, of course. I am software architect, and I have more than 25 years creating enterprise solutions. And today I am the CTO of the Quantum company, a company specialized in quantum software. And for me, it's a privilege to stay here with you. And I will do whatever it needs to put you today to these technologies.
Well, and hello everyone. My name is Juan Moreno. I've been with Amazon for nearly 9 years. I'm part of the quantum computing team in AWS. I am a solutions architect that specializes in the Amazon Braket product, which is AWS quantum computing service. And what I'm going to do with you today is to give you a little bit of a hands-on feel of the software and the approach of AWS to quantum computing. Mihit, should I take it from here?
Yes, please.
Okay. Let me share my screen.
Mm-hmm.
All right. So that's our agenda for today. We just finished the introductions. The first thing I want to do is to set up the hands-on environment. So the reason for this is because even though we haven't explained anything about Amazon Braket is, what Amazon Braket is, I want to make sure that you spin up a few things and you get your development environment ready by the time that we are finished with the theory and we are ready to start typing commands in the console. So for that reason, maybe this will feel a little bit awkward, that you have to follow a few steps that you don't quite understand why you are doing it. But don't worry, bear with me. Everything will make sense after you have completed the steps and I have covered the theory. So I would like you to open a browser, first of all. I'm going to switch to my browser so you can see my screen. Can you see my browser there?
No, we cannot.
Okay. Let me see.
Now we can.
Yes,
You
now
can
we
now?
can.
Okay.
We can. Yeah.
Great. There's a little bit of delay. What I would like you to do is to type this this web page on your browser is dashboard.eventengine.run. I'm going to paste it on the chat as well and hit enter. I have too many windows open in my computer. Bear with me. Here's the chat. That's for everyone. Please go ahead and go to that website. The next thing I want you to do is to enter this hash code that I'm going to put in the window under the terms and conditions. That's the one that I pasted on the chat. Just copy that and accept the terms and login. What we are doing here is to give you access to a full AWS environment with an AWS account that is going to allow you to play with the platform for the next not only 2 days but 3 days. We are going to leave the environment open for you, so after the event you can continue practicing, going deeper and play as much as you want with both Amazon Braket and QuantumPath. Okay. One recommendation I have for you guys here is that try to use a private browser, or make sure that if you have a previous AWS account, you log out from your existing AWS account, so the sessions do not mix and you don't have problems accessing the lab environment. Needless to say that this is completely free. You are not going to be providing any credit card details or any other personal information for you to be charged for any money or anything like that. This is something that both the teams of Quantum and Amazon are glad to give you access for free. Please go ahead and enter the email one-time password, or OTP. And after you do that, you will see a screen with an email address option. Just type your email. If you don't mind, try to use the email that you used to register for this event, but any email that you can check your inbox right now will do. The only thing I have to ask you is that that email address is something that you can receive emails immediately, like right now. Because after you click on send the passcode, you're going to get an email on your inbox with a 9-digit code. And that code needs to go over here on this screen. Be patient. I've never seen that these emails go to the spam folder, but sometimes it takes up to 10 or even 15 minutes for some people to get this email. So if you don't get it immediately, don't panic. The email eventually will arrive. Unless you have any problem with your internet settings or whatever, you should be receiving that email soon. I'm going to go ahead myself and open my email to get my code. If you have any problems so far to see the web page or any of the steps, let us know in the chat. My colleagues will be glad to help you. I see that I have received my code already, so I'm going to paste it here. And after I paste it there, I will click on sign. Okay. Please don't reuse my code, or you will steal my session otherwise. No, you will not. It has to be with the email, but Interesting. Says that the event is inactive or is at capacity. Let me take a look to that. Maybe we should use the second event already. If you are seeing the same error that I'm seeing,
Juan, we have 230 participants, so
okay.
probably.
I will provide the access to the second hash and the third hash as well. Bear with me, guys. So those of you who are seeing the same message as I'm seeing in the screen, I'm going to give you a second hash that you can use right now. Please go ahead and use that second hash that I just pasted on the chat. That should give you access to the platform. I'm going to grab one of the seats myself. But don't worry, there's a space for everyone, for almost everyone. We have 300 accounts. So it should be plenty for everyone. So after you enter the hash, put your email address, receive the 9-digit code, place the code in place, and hit and submit, you should see a screen like this one. I want to ask everyone to please hold on a second before you go into any further steps, because there is a few key pieces of information that you need to copy in your computer. And for some cases, there will be only one chance for you to copy that information. So I know that many of you might be anxious to go ahead and continue forward, but let's go everyone together on this so we don't have problems later. Thanks for your patience. How are we doing on the chat? Are we having any more problems to access?
It looks good so far.
Okay. Great. Thank you guys for the feedback. Really appreciate it. Don't be shy at all. Keep talking in the chat so we know whether we are doing the right things. If you want us to slow down, to speed up. Perfect. Perfect. Thank you very much for confirming that. Fantastic. I'm going to continue ahead. If any of you have a problem with invalid hash or the session is at capacity or things like that, let us know, and my colleagues will provide another hash for you to try. But you should be okay. Click on AWS Console. Now from here, you don't need to copy any of these details because we are going to use them in a different way later. You can kind of ignore this screen and directly click on Open AWS Console here. And ta-da, we are in the console. You can either choose the new console or the old one, whatever you prefer. Both are okay. I'm going to click on choose the new one just because I like the interface. It's nice. And here you will see a screen very similar to this one. The first thing we need to do is to activate the Braket service, which is our quantum computing service. So to do that, I can type here on the top search window or box the word Braket or Amazon Braket. And you see there how the first result is Amazon Braket service. I'm going to highlight it there as a favorite because I'm going to be using it these 2 days. And click on it.
One quick request. Can you make the text bigger?
Sure thing. Thank you, Nihit. This is the welcome screen of getting started with Amazon Braket. To store our experiments, our quantum computing experiments, you're going to need to create text files with the result of those experiments. And for that, we use the storage unit in AWS that is called S3, an S3 bucket. For those of you who are familiar with AWS, probably you know already that we use Amazon S3 or a simple storage service for many things and many services. Amazon Braket is not an exception on that. So the first thing you need to do is to create a bucket with all that information is going to be stored. My recommendation is that you leave the default option here and copy and save in a very secure place this bucket name that is being proposed by default to you, because we are going to need it later. When you configure QuantumPath, you will need that bucket name. If you want to create your own bucket with your own name, that's totally okay. The only requirement is that the beginning or the prefix of that bucket is Amazon-Braket, dash and a string. But other than that, I'm going to copy this name for myself. We can retrieve this later, but it will be cleaner if you put it in a safe place now, so you don't have to worry about it later. I'm going to copy my text box here. And then if you continue scrolling down, you can ignore the account permissions. This is just an informational message about what kind of access you are going to get. And then you have to accept the terms and conditions of the service. All right. After you have done that, you can just go ahead and click on Enable Amazon Braket. It should take just a few seconds. Okay. I'm going to go back to the console and repeat these steps. Let me first let the service to finish. All right. You should see the main Braket window now, but I'm going to repeat again these steps for those who didn't get it. So I was in the event engine window and I click here on Open AWS Console. That was the first step. After that, I came here to the search window and I typed Braket. And that gave me access to Amazon Braket service. You can also save it as favorite if you tick on that little star on the right-hand side of the name. And after I click on that, I'm not going to see that screen anymore because I already accepted the service. But when you click on that for the first time, you will see a welcome window that asks you to create an S3 bucket, give it a name, and accept the terms and conditions of the service. My recommendation is that you accept the bucket that gets offered to you by default and save the name in a notepad or wherever you have as a text editor and save it. Click on accept the terms and conditions. And after you hit accept, you should be able to see this screen that I'm seeing right now. Bearing in mind that Braket is spelled as B-R-A-K-E-T. It's not Braket with a C. This is because of Leo Dirac's quantum computing bracket notation that refers to the bracket mathematical notation. There's no C on the name. Perfect. Let's move on. So we are in the devices page. We are going to cover this page extensively later. Don't worry about it for the moment. What I want you to do is to go to notebooks. It's the second link on the left-hand side. You will see an empty screen with no notebooks on it. What I want you to do is to create a new notebook. You can use for that either the button that shows on the right-hand side of the screen on the top or on the bottom of the screen. I'm going to pick this one and create notebook. Here you can give any name that you want to your notebook. You can call it your name, lab, workshop, whatever you want. I'm going to call it by my name, Juan. For the instance type, you can leave the one that is there by default. You can pick any other instance, but the T3 medium is a big enough instance for the type of exercise that we are going to be doing today. You don't need to modify anything on the rest of the screen. Additional settings, the roles, everything can be left as it is. And after that, click on Create Notebook Instance. And that will start creating a notebook instance that is going to take maybe 5 or 6 minutes to spin up. And that's the reason why I wanted to do this at the beginning, because while that is running and start to get ready, we can actually go and talk about the theory. There is one more step that I want you to do after you have created your instance. That is to create a user, an AWS user, that we will need later when we do the integration with QuantumPath, with our friends in Quantum. To create a new user, again, go to the search window on the top and type IAM or EIM for those of you who are Spanish speakers. You will see that the first option is the Identity and Access Management Service. Go ahead and click on it. And there, you can go to the left-hand side of the screen and click on Users. You will see that there is a default user created there. We will use it for this graphical environment, and that's okay. But we want to create another one to use later. So on the right-hand side, I don't know if you can see that. I cannot see it very well, so I'm going to minimize this. On the right-hand side, there is an Add Users button. I want you to go ahead and click on that. Let me resize my window. And don't worry, I know I'm going slow, but this is just at the beginning. Things will get more exciting and interesting in just a few minutes. As the username, you can give to that user any name you want, whatever you want. Again, I'm going to call it Juan because that's my name and I like it. For the options that you see below, we just need the access key or programmatic access. You don't need to tick the other box. Only name and access key, programmatic access. I'm going to stop for a second there to make sure that everyone catches up. So we type IAM in the console, click on IAM. On the left-hand side of your screen, you see there are a few menus. One of them is Users. You click on Users. There you will be taken to a screen that you see just one user. That is the default one. We want to create a different one. So we go ahead and click on Add User. And that is the place where I am right now in this screen. I just gave my user a name. And this is important. For the credential types that you see on the bottom of the screen, please just tick access key, programmatic access. This is very, very important for later, for you to have access later to a quantum platform later, okay? Let's click on permissions. And here we can go to attach existing policies directly. So you can ignore the first two squares and click on the third one that says attach existing policies directly. The difference between IAM and the Braket service is the Braket service is the quantum computing service for AWS that we use to create quantum experiments. IAM is another AWS service that just allow us to create users and groups and assign roles and permissions to the entire AWS platform. We are not going to be going deeper in IAM today at all, we just need it for the first few minutes in order to create a user that is going to allow us to use both Amazon Braket and a Quantum platform. I'm going to click on Administrator Access in the policy window. So that way we get full administration privileges for that user. Okay, that's the only window you need to, the only box you need to tick. All right. I'm going to finish creating that user, and then I will review everything again with you guys to make sure that everyone is in the same place. After I click on that box, I just go to review. I don't need to modify anything here. This is the policy I want, and finally create user. You don't need to touch anything else on the other windows. Now, I have created my user. Now, I cannot stress enough the importance of this point. I want to make sure that everyone is here and everyone is with me at this point, because this is a critically important screen. I want you to copy this access key. You can click on this little icon that shows on the right and copy it somewhere, maybe besides the name of the bucket that you created before, in a text file. Do not lose that access key, because if you do, there's no other way to retrieve it later. Well, you will be able to retrieve the access key, but the secret key that shows besides, this is your only chance to take it. So what I want you to do is to click here on Show your secret access key, and when the string shows in the screen, I'm not going to click it myself so I don't reveal my password, but when you click on that, you will see another string, very long one. I want you to copy that as well and paste it in a safe location together with your access key and your bucket name. If you lose that secret key, you will not be able to access the platform later. You will need to create a new user and repeat all these steps in order to do it. Not the end of the world, but it's better to do things right from the beginning so you have a better experience later on in the workshop. Okay. So what I'm going to do is I will create a user for myself later and do it so I don't have to do it here while I'm sharing my screen. I'm going to close. And with this, we have our environment ready. I see that WebEx doesn't give me an option to share files, but if you guys who are helping me find a way to share files with WebEx, you can share the PDF that I shared with you earlier for everyone to follow the steps in order to set up their environment. Just a quick reminder, we used Event Engine in the initial link that I gave you, and maybe I will switch to my slide to show you that part. We use Event Engine with one of the two hashes that I gave you. You use the one, either of them should work. If not, let us know. Enter the hash. After that, you have to select the OTP option or email one-time password. And after that, you have to enter your email address, as you can see in this screen. When you enter your email address, you have to wait for a few minutes and you will receive a code. It's a 9-digit code that you have to enter here in this screen. This is just an example. Do not use that code in the screen because that will not work. You click on Sign In, and after that, you will be presented with this screen, a dashboard where you just need to click on AWS Console, and after accepting the next window, you will be presented with the general AWS window, and from there, you can search for Braket, accept the service, accept the default bucket that is presented to you, and after that, you can launch a notebook from the main console. The notebook menu is on the left-hand side of the screen. While the notebook is running, you can go to IAM or EAM and create a new user with any name that you want, and make sure that you assign the administrator access policy to that user. Very, very important. Make sure that you copy the secret key and the access key for that user. The secret key is only available once at the time you create the user. You will not be able to retrieve it later. So make sure that you copy that user in a safe, that password in a safe location. Okay. Awesome. Well, while people are getting ready and you finish that stuff, I'm going to give you a couple of basic concepts before we get into the actual theory. I wanted to cover the cost estimation and how costs work in AWS, because I think it's important to understand how the pricing model works in Braket. It's a bit peculiar, so it's something that we like to cover first. Don't worry if you don't fully understand everything yet. This is just for while people are getting the environment ready and resolving their last problems, to start covering some material, but it will not be a big deal if you miss this part. In Amazon Braket, we divide the actual workloads into shots, tasks, and hybrid jobs. These computers work in a way that you have to write a circuit in many cases. It's not the only way, but often you have to write a circuit like digital computers 40 or 50 years ago. So you have a wire and you set up different gates with the NOT gate and the IF gate or things like that. And then you have to execute that circuit. Whenever you execute that circuit, we call that a shot. So we are presenting our wires with a number of logical gates. We run that code, and that's a shot. Now, because of the probabilistic nature of quantum computing, one shot is never enough. You need to have a statistically significant number of shots in order to have a probability distribution in your results that will be meaningful to read and to operate on. For that reason, we usually do 100, 1,000, 10,000, even in some devices we do 100,000 shots for one single experiment. So we group all the execution of those shots into a single task. If I'm running an experiment, I create my task and I say this task is going to run 1,000 times, and that's 1,000 shots. That's how the service is charged, basically. You pay for the number of tasks that you create, and you pay for the number of shots that you create. It happens that there is a higher level of complexity on this, especially when you are working with hybrid algorithms, where a digital computer or a traditional computer works in combination with a quantum computer to resolve a problem. You might need to run many tasks, especially in the so-called variational algorithms, in order to achieve a meaningful result. This is relevant in fields like machine learning, for example. In quantum machine learning, you are trying to reduce the cost function of a problem, and for that reason you need to do an approximation to the minimum state of energy that will give you the best result. So many tasks are needed in that case. So that's why we created the concept of hybrid job, where basically on top of the shot and on top of the task, we create another logical unit called the job that groups tasks together for a single experiment. So I might have a very big project that runs dozens of tasks and hundreds of thousands of shots in order to obtain my results. And we group that into the job. In terms of pricing, you don't need to worry about the jobs. You only pay for the shots and the tasks. Obviously, if you are using traditional resources or classical computing, you need to spin up other classical resources to do that. And you use Amazon to do that, AWS, you will have to spin up the EC2 service for computing. But that's something that gets charged separately, but not directly related to quantum. So here's an example on on an annealing problem. This is, instead of a circuit, is a different type of device that also works with tasks and shots. We will see what are the differences between both in a second. But basically, you can see there how if I run an experiment with 10,000 shots in one task, the total cost of that will be around 220 American dollars. Okay. And if you increase the number of shots or the number of tasks, you can just make the multiplications and predict what your total cost is going to be. So it's very easy to know before you start any experiment how much that's going to cost you. Hopefully I will be able to show you with a notebook here. In the next example, we have the cost of a simulation. Simulators are another type of device that we have available in Braket. Again, I'm going to be covering those in a second. And those get charged per the minute. So you see the minute rate there, less than 10 cents per minute, 0.075 American dollars. And if you have, for example, a simulation that lasts for 30 minutes, well, the good news is if you are in the first year of your usage, so when you open an AWS account, you will not pay anything for that. Because for the first year, you can have 1 hour of free simulation with the platform. Okay. If you continue using the platform for more than 1 hour in a given month, or after the first year, then you will be paying the numbers that you see in the screen. Here, the number of shots or the number of tasks that you execute is not relevant anymore. It's just the time that your experiment takes to run. Let me see if I can show you this in practice. Bear with me 1 second because my session expired and I have to start it again. In the meantime, feel free to put your questions in the chat. My colleagues will help you. It will be very apparent and very easy to see the differences between simulators and real quantum computers after I show you a couple of examples. I wanted to give you a feel of how the platform looks like before you start playing with it. And I'm going to use this cost estimation as an excuse to give you that idea. This is a typical notebook in Amazon Braket, where you can not only write code, but also you can put text on it. So it's very useful to create dynamic and very educational type of code that allows you to understand what you are executing at the same time that you are reading it. For many of you, this might be very obvious and you are more than used to work with Jupyter. For those of you who are not familiar with it, just follow up with me. And this is just a demonstration that I'm going to do for you. Later, you are going to be able to type your own commands and we are going to be interacting with real quantum computers. Here, you can see the pricing structure and in the table that you see in this screen as the pricing of all the devices as I was mentioning earlier. We can share this notebook with you later. What I'm doing here is to export a few libraries of the Amazon Braket SDK that I will cover later as well. And defining a function that the only thing it's going to do is to actually ask for the price for the task and the shot, as I explained in the previous slide, using the programmatic access that the SDK gives us. When I execute that function, I have everything ready to basically run a few circuits and understand how much they're going to cost me even before I run them. Here, I'm just exporting a few math libraries to present my results and also the basic Amazon Braket libraries. Again, we will cover that in detail a bit later. We are defining a new circuit here. I will cover the details of this circuit again later when we go into the hands-on session, but this is a very simple circuit that is taking advantage of the special properties of quantum devices like superposition and entanglement. And this is what I'm doing in this piece of code. I'm defining a circuit, as you can see in the ASCII print there. I decide 1,000 shots. Did my screen stop working? Are you still seeing my screen?
No, cannot see your screen.
Oh, I don't know what happened. I'm gonna try to share again. I didn't touch anything, I promise.
Back up.
All right, well, let's fly through this so we can get started with the theory. As you can see here, I'm defining the device that I want to use. You will understand what is that in a second. And I'm basically asking how much it's gonna cost me. For this type of device, the Rigetti device, that is one of our quantum computers, we see that for one task and 1,000 shots, I'm gonna be paying 64 cents or 65 cents rounding. And you can see the price per task and per shot here. This is to show you that in Amazon Braket, everything is programmatic and you can get all the information you need just by code if you don't want to use the graphical interface. Okay, I'll show you how to check pricing in the graphical interface as well. If I use a different type of device, like an ion-trapped type of quantum computer, like IonQ, which is another device that we offer in Amazon Braket, you can obtain the same information and you see that the cost estimation for that is $10. After I know how much it's going to cost my experiment, then I feel much better to start actually executing things, knowing that I'm not going to go over the pricing or that I'm not going to get a surprising bill at the end of the month or things like that. That is sometimes that customers worry about, rightfully so. What I'm doing here is to define a local simulator that is completely free, just to make sure that my numbers make sense and I'm executing my code that I created earlier in that circuit in this cell and representing the results. Don't worry about what you see in the screen. It will make a lot of sense later. If you are not familiar with this piece, I will explain it in detail. All I wanted to share with you is that these are the best practices that we recommend to every customer. Execute your code. Before you execute your code, before you run your experiments, know how much your experiment is going to cost, and that way you can be ready and have the peace of mind that it's not going to be a surprise on the actual cost of the experiment. Okay, this is running now in the quantum computer. We're going to leave it here running, and we will get to how to check things that are running on the machine and all that later on. But with that, I'm going to finish this part. You know now how the pricing works, how to get access to your notebooks, and how to start using the first basic libraries. That was the whole point of this initial demonstration. What I'm going to do now is stop for a second to check some questions that there might be in the audience. And after that, I will start the theoretical part of what is quantum computing, what is AWS doing in this space. Any questions that you guys and my helpers want to pass me of all the chats, or should I just go ahead and take a look myself?
I can moderate one if you'd like.
Okay. Is there anything interesting, or do you think that I should be answering right now?
Yes, one very interesting question. Is the note available somewhere? Is the notebook available somewhere?
Is the notebook? Yes. So this is a notebook that I built, and so it's not available in any GitHub repo or anything like that. But after this event, we are going to package together the PDF with all the presentation, and also we will attach the notebook so you will be able to open it and play with it.
Okay. Another question is about budget. Is there any option to set up a fixed budget so it does not go over a limit?
That's an excellent question. You can set an alarm on your billing. So whenever you reach a certain amount, you will get an alert. It will not take an action to stop or cancel your experiment though. It's a manual action, but you can set up an alert on billing after a certain budget.
you. There are some deeper expert level questions too. Should I answer them? Should I ask you now or should we wait until later?
We can give it a shot. Give me one and see if I know it. And if I don't, I will let you know.
Okay. If I'm using Penny Lane with a QML approach, can I use the estimation tool inside the code?
Inside the code, yes, you will be able to do it as part of your code and you will get your output before the code runs. That's totally possible. For the case of Penny Lane, yeah, it depends on the device that you use. Usually for Penny Lane, I've seen more used with simulators. So you will be able to use the AWS pricing API to get the cost per minute for a simulator and present it in your code. And you can attach logic to it. So things like do not run the experiment if the estimated time is going to be more than X minutes or X amount of dollars. The thing with Penny Lane experiments and QML is that it is important that you set up a maximum limit of tasks that you are going to run. If you leave your function free to minimize itself, you might hit a barren plateau where the function never minimizes and your experiment runs for hours and hours and days if you don't stop it. So that's the only best practice in terms of coding that we recommend for people running QML, to set up a limit on your minimize function.
Okay. This is about D-Wave next. So for D-Wave, is the number of shots equal to the parameter number of reads?
The parameter number of reads is the number of passes that you will do on your annealing problem, and I think that matches with your definition of reads. Yes, so up to 10,000 shots that you have, it will be the number of times that the mapping of your problem in the annealer topology gets read or gets executed, if I got your question correctly.
Okay, another question. Amazon has quantum computers, or is it just a platform to access various different quantum computers?
Today is the former. It's a platform to access several quantum computers, but we have 4 simulators that I'm going to be showing you now that are Amazon Braket build, and also we are working to build our own device. It's not available today, but it's a superconducting based device that is being built at the moment in our Center for Quantum Computing in California. That will be available in the future.
Okay, I think those were all the questions we had.
Awesome, thank you, Nihit. Let's get started. I love the questions. I see that it's a lot of variety in terms of the technical knowledge about this technology. I'm going to try to cover materials in a way that makes everyone happy. For those of you who are super familiar with quantum computing, bear with me. For those of you who are completely new to this technology, please feel free to ask your questions and ask me to slow down if you feel that if you feel you are getting lost. I will try to, as I said, keep everyone happy. So first of all, I want to explain to you guys what is AWS doing in this space. Where are we in this space? We are very excited about the potential of quantum computing. We believe it's going to be a disruptive technology and has the potential to revolutionize how we do computations. But at the same time, we are very humble about all the scientific and technological challenges that quantum computing poses today. We know that we are many years ahead to probably have a fault-tolerant quantum device that can work at the same level of efficiency and reliability than a normal digital computer. So we like to be very clear on that messaging. There is no production workloads running in quantum computers today. And no, you cannot move your Oracle database or your Apache web server to a quantum computer today. The machines are not ready for that, and they are not supposed, or they are not meant to be built to run that type of workloads. Quantum computing is a different type of computation. that it leverages the laws of quantum mechanics. And as such, they are built in a different way, and they have the special properties or take advantage of the special properties from very small particles. Often we are dealing with atoms, electrons, photons, subatomic particles that we use to create those ones and zeros the same way that a traditional computer does in order to read our information. But you might be wondering, well, if I'm just dealing with ones and zeros the same as a digital computer, why are they so good, or why are they people talking so much about quantum computers? The reason is those quantum mechanics properties that are only valid when you get out of the traditional physics or the Newtonian physics. Properties like you probably heard about, like superposition and entanglement, that allows you to have a superposition of states of 1 and 0 while you are taking a calculation. And that makes certain type of problems to run much more efficiently in a quantum computer than they can in a digital computer. Same as entanglement. When two particles get entangled to each other, what that means is that reading the result in one of them will tell us something about what the result on the other one is going to be. And that allows us as well to speed up calculations and grow exponentially when we add new qubits to the machine, the number of calculations that we can do in one single step. You heard me saying the word qubits. That's the short for quantum bits, which is the equivalent to the bits in a traditional computer, but again, have these special properties that allow us to run computations in a different way. I'm going to be covering in the notebook that you spin up earlier a piece of code that will take advantage of these properties. So you will see all these things working in real devices today. Okay. With that super short, brief introduction to quantum computation and quantum computing, I'll explain now what quantum computing at AWS is about. We divide our service in 4 different pillars, as you can see in the screen there. One of them is the one I mentioned earlier to answer one of your questions, the AWS Center for Quantum Computing. This is a research center that is located in California and in the Caltech University, or the Institute of Technology for California. Where we are putting together basically the top researchers on the field working there in order to try to come up with better algorithms from the software point of view to reduce the errors that these machines produce today. So to create basically good error correction for qubits, but also to try to come up with a good design for a new quantum computer and make our contribution to the hardware side of things in this community. If you are a little bit familiar with this field, you might have heard that there's a lot of players and there's a lot of people with different ideas. Papers are being published every week. This is our contribution to that community and to that scientific effort that is necessary to advance this field. Then we have the Quantum Solutions Lab there on the top right-hand side. This is our professional services team. So basically, if you are working on a problem, you have certain ideas on what your optimization should look like, and you suspect that quantum computing could be a good fit for that problem, we can engage with the Quantum Solutions Lab and help you to work from your problem backwards to figure out a good POC or a good solution to your problem that maybe would be a good first stone for the time when these computers are available and we reach fault tolerance for you to put this one day in the future in a potential production environment. But we don't stop there. Basically, what this team does is basically talk to you, see what are your needs, and maybe map your problem into a high-performance computing problem or maybe a machine learning problem, and find an algorithm or a solution that works for you and fulfill your needs, basically. It's just about getting you quantum ready, whatever that quantum ready means to you today. And that's what the team works on. Then we have a partner network. Probably this is the best event to show an example of that. Quantum is one of our partners. It's an excellent integrator between the power of different devices and what Braket offers, and a fully seamless programming environment where you can basically, with a very easy interface, create your circuit, execute your experiments, and focus, if you are an experimentalist or you're a theoretical physicist, only on your Hamiltonian, your experiments, and don't worry too much about having to learn how to code in one hardware or in a different type of hardware, and so on. The same as Quantum, we have other partners that specialize maybe in chemical simulation of particles. Others specialized in the financial sector. If you are looking to do an optimization approach to things like fraud detection or portfolio optimization for customers, we can put you in touch with different partners. And finally, Braket, which is what we are going to be spending most part of the time today, right? Amazon Braket is a fully managed quantum computing service. And the great advantage that we are going to see very, very soon is that you can change the endpoints of the different quantum computers. And with one single piece of code that you will learn, you will have access to 4, 5, 6 different devices without having to learn the gotchas, the documentation, and all the different in and outs of many different devices. I will be covering those devices, hopefully in deep enough detail, and we will be running today an experiment or an algorithm in various of those devices, and you will be able to retrieve the results. And that's what Braket is about, right? It's a platform where you build and then you test. And to test those things, we give you simulators that you can use. And then after you have tested in simulators and see that more or less that the results make sense, you can go ahead and try with real quantum devices. The simulators are great because allow you to play a lot more with different parameters and run much bigger computational problems that you can in a real quantum computer nowadays, because as I said, the machines are still in a very primitive status, right? In a very primitive state. After you have run your experiments, you have a full environment that allows you to analyze your results, to see your experiments, and to check things in a very big text files where you can see everything that happened, right? So it's a very end-to-end platform where you basically have everything you need covered. And we will see later on how QuantumPath from Quantum adds even more value on top of the platform. That will be the whole day too. I've been talking for a while now about simulations, and you might be wondering, what exactly is that? What do you mean? A managed simulator is basically a piece of software that runs in a traditional computer, but that simulates the effects of a quantum computer. Remember that I said that we have to execute several shots, and that we need a probability distribution and an energy wave that contains all the probabilities of your problems in some cases, and we can rate the results in different ways. And there's other simulations we can do. To cover what we have in the screen, it's good for you to know that we have the local simulator, first of all. When you download the Braket SDK from our GitHub repository, if you don't mind, of some of the people who are behind the scenes helping me, if you don't mind to paste the link to the GitHub repository, that would be great for people to be able to download Amazon Braket. You can download that, and you can even forget about the actual graphical environment. You can run in your development environment that you are used to with your graphical editor or whatever you have. Install those libraries and start making simulations without having to pay a penny for it. The local simulator is completely free, and it comes integrated with the SDK itself. So it's a very good way to get started and do fast prototyping, up to 15, even 20 qubits, depending on the depth of your circuit. Then if you want to do something more evolved and more complex, you have the state vector simulator. That simulator can simulate up to 34 qubits, and it will store the entire wave function of your problem with all the probabilities of it, even the very unlikely ones. So the good thing about these managed simulators is that they are running in the background, are supported and managed by AWS, and you don't need to worry about the spin-up resources, infrastructure, and stuff like that. You just set up your endpoint and launch your experiment, and everything will be scaled behind the scenes for you to return the result. It has certain parallelism, so you can run up to 50 threads in parallel. So it's a very powerful simulator. Going one step further, we have the Tensor Network Simulator that is more powerful, allows you to run up to 50 qubits. And with this simulator, you can map your problems as a graph. And once you have that mapping done, this simulator will try to traverse that graph in the most effective way to give you the results back. So that means that not the entire probability distribution of your problem is going to be stored, but only the possibilities that are most feasible or more realistic, right? From an optimization point of view. Internally, it runs in a couple of phases. First it goes to a rehearsal phase, and then it will just collapse into the final results that get presented to you. And if your problem that you presented was too complicated or too difficult, it will let you know with an error before it runs any farther, so you can optimize your time. And finally, my favorite, the density matrix simulator, is the noise simulator based on the density matrix formalism and the Krauss formalism that basically allows you to create noise channels to simulate how a real computer will reply in reality. You can create your circuit and then you introduce things like bit flips or phase damping or any other types of errors that are going to return results that are dirty, that are not pure states, but also mixed with what they are called mixed states, right? And that's possible to do with this simulator. Now, in terms of quantum computers, this is the exciting part, and probably why most of you are here today. We are going to play with these devices. We have a quantum annealer, which is a different type of technology to the, I would say, most people when they talk about quantum computing, for the lay person, they think about circuits. But D-Wave is a very powerful device and also very good suited for optimization problems, right? The quadratic and constraint binary optimization problems in particular. This device, we have two versions of it, one with nearly 3,000 qubits and another one with nearly 6,000 qubits. And it's available 24/7 in the platform, and it's based in superconducting loops. It's a special type of technology where the small metal plates are refrigerated or cooled down to very, very low temperatures, so to the point that they exhibit these quantum properties that we want in order to read our data from them. You map your problem into the device and then you let it anneal or come down to the lower energy state in order to get your solution. In that sense, it's not wire-based, it's not gate-based as the others. The other two devices, IonQ and Rigetti, they are universal gate-based. They are based in different type of technologies. IonQ is based on trap ions. Basically, in the version that we have is the 11 qubit version in our platform. You get an atom of ytterbium, and then you create an ion with that, and you use laser tweezers in order to fix the atoms in place, the ions in place, and get your readings depending on the polarization of the particle, and read your ones and zeros. We will see the topology of these devices really, really soon. And then for the Rigetti device, it's again based in superconducting, same as D-Wave. However, this is a gate-based serial type of device. And again, the hardware properties are similar, but the way the circuits are executed is different. We have a new device that we recently added, the Lucy device from Oxford Quantum Circuits. Is an 8-qubit device, also based in superconducting and universal gates. You will see it in the platform. You have access now, so feel free, if you get bored of all this theory, you can start playing around in the console, go to the devices section and start exploring yourself. And a new device that is coming, the Quera device, that is based on a new technologies, analog Hamiltonian simulation based on a special type of atoms, a full atom in Rydberg states, and it's going to be very, very useful to simulate real quantum systems as they work in nature. So in that sense, it's an analogic simulation that is coming later this year. You already heard me talking about the shot, the task, and the hybrid job. So you understand now that to execute a task in a machine, you have to decompose that task in a number of shots. And with that, I can show you the console around. If you have questions, please go ahead. If there's anything that I should be answering at this point.
No, all good so far.
All good? Okay, great. I hope that you're not getting too bored. It's gonna be practical from now on. We left this thing in the IAM user. If we go to the Braket platform, as out of curiosity, let me check if the notebook is there. Yeah, the notebook is already in service. So some of you, most of you, or all of you should see that this notebook in service. But before we go into that, let me show you the QPUs.
Juan, we got a couple of questions. Do you want to take them now?
Yeah, please, go ahead.
Okay, all right. First one, how do we know which one is the best for our purpose? Is there a guide for it?
That's an excellent question. There's not a prescriptive guide per se. When you are starting with your first circuit, it's a good idea to run it in different devices to see which one works best for you. Different devices have different properties, so some of them have very high speeds on how the gates are executed in terms of speed, and they are slower on the readout later. Others are the other way around. They execute the gates in a slower pace, but they're very fast in the readout. Also, the type of problem that you have makes a big difference, right? If you are dealing with a problem that, as we call it, an optimization problem, when you know very clear how to map your problem in some type of graph, it's good to use an annealing device for that, because you can basically map your problem in the number of qubits that you have. As you can see here, the annealing device has like nearly 6,000 qubits, and that allows you to map a problem in this device in its topology and run it this way. But other problems are more suitable for the serial gates. When you are starting, it's a good idea to give a shot to a few of them. And it's only when you get into more complicated or more complex algorithms when these things start to make a difference. I will provide a couple of notes on the differences between the Rigetti IonQ and OQC, so probably that will shed a little bit more light on that question.
Okay, thank you. Related question. Why are there so many different simulators?
Right, because that's another good question, because the type of problems that you're going to be running or interested in running are different, right? Some people are interested on see how the effects of noise in a device are going to affect the results before they run them, right? You will see in today's hands-on lab how quantum computers return errors and not everything that we expected. So some people like to use the density matrix simulator first in order to have an idea on how those errors are going to affect their results. And then also depends on the complexity of your problem. Your problem might be big enough that it doesn't fit in a state vector simulator. You are storing every single possibility of your result. You might want to just do a more optimized way and only pick those results that are relevant or important to you. So that's why we offer also the Tensor Network Simulator to present, to map that type of problems. Usually the state vector simulator is the best one to start. And from there, depending on the complexity of the problem or what you want to achieve, you have the other options.
Okay. Another great question. Do you have simulators for D-Wave?
I was about to say that in my previous question. Thank you. No, we don't. We don't have digital annealers today. There's a couple of good ones in the market, but there's nothing available in Braket per se. However, the D-Wave device itself comes with a simulator if you want to use that, and there's a specific plugin for it.
Okay, that's it then. Thank you.
Thank you. I love the questions. They're very good. All right, let's take a look to, today we are not going to be dealing with annealers. Probably one thing that we can do is to explain some of these windows. As you can see here, I love that this window is here today because you will not be able to see this often. You see that this device, D-Wave, is offline and unavailable. D-Wave is carrying maintenance work on this machine today. So later tonight, this machine will be online again. These two machines from D-Wave run 24/7, so they are always available. This other machine is available right now. And as you can see here, you see the number of qubits, the availability status, and when it's going to be next available. If you see here in Lucy, the next availability windows is in 17 hours. What that means is that the machine is there, it's active. You can use it and send your code to it. But the code will not be executed until the next availability window. So in most cases, that means that you're going to go into a queue, and in the next window, your code will be executed. Let's take a look to some of these properties. IonQ, for example. You can see the hardware details in a much more detailed way that I explained earlier, if you are curious about that. I love the hardware part, so I could be talking for 3 hours about how these things are built, but let's cover everything. The availability window, you see it here. The region where this device runs, this is important because devices are regional. And as you can see in your environment, you are right now in US East 1. Depending on the device you want to run, you will have to find your task once you have executed your code in the right region. As you can see here, all the other regions are grayed out, and Braket and their devices are available in US East 1, US West 1, US West 2. And if you go farther down, this is EU West 2, which is our first device in Europe, and it's located in London. That is Oxford Quantum Circuits. You have the cost here, the number of qubits. We covered all those things before. And check this topology. This is super interesting. These 11 qubits are interconnected in a mesh, so there's the same distance between all of them. And for that reason, the calibration window is pretty straightforward. You can see the fidelity between these gates and per qubit and per pair of qubits, which are the two key parameters to do benchmarking in these devices. How good or how reliable are the readings of every single qubit, and when you pair two qubits together. And those are the main metrics in a very, very simple way to calibrate the device. You can use this window as a reference. The best thing to find the value and to answer probably some of the questions that you were having about what machines should I pick is to check the connectivity in another device. Let's pick this 80 qubit device. This is the largest device available in the internet today. There's nothing bigger than 80 qubits that is fully available and ready for customers to use in today's quantum space. This is the topology for the Braket device. And as you can see, it's a bit different, right? It's not everything interconnected. There's these rings that connect to each other in a next neighbor model. And that's how this device connects. That makes the calibration window a little bit more evolved, because every qubit has a different fidelity, depends on the neighbor, and you can see for the edge specs here how two qubits connect to each other as well for each one of the connections. So this is very useful when you are running circuits and you really care what qubit you want to use. So as you can see, there are benefits, pros and cons on each model. Here, this device allows me to actually pick which specific two qubits I want to run on my circuit, and we support that. One thing I haven't mentioned so far, and is super, super important, and please take note of this because this is going to be relevant for later, is the device ARN. Like everything else in AWS, there is an Amazon resource name that you will need to run your code. You will see how easy it is to create a piece of code, define a circuit, and then just change the endpoint to indicate in which hardware you want to run. This ARN is the actual pointer to that hardware that you will use in your code later when you want to execute your algorithm. Okay. And finally, let's take a look to Lucy. 8 qubits. The topology is similar. They are all connected in a ring. And this is the calibration window for Lucy. You can see the fidelity of the gates and the speed of the readout and all that. Okay, so when we start playing with the platform, we will be playing a lot with this tab, the tasks tab. And you will see how your experiments start to pile over here. And bear in mind that you will be in different regions. Our event engine only supports US East 1. So this is the region where we are going to be mainly be operating. So everything that we run in US East 1 will be executed over here, and you will be able to see it. And finally, this is the jobs task for the other logical construct that I was mentioning earlier. We will not be doing any job today, but this is where the platform is, and the link is if you decide to play with it in the future in your own account, and that's where you can find it. Okay, I covered the entire console. There's one thing that I forgot earlier, and I wanted to mention before I open the floor for questions again, that it was about coast. Let me show this in my actual device. I'm going to bring this here. Let me make it a bit bigger. When I talked about Coast earlier, I forgot to show you the Coast Explorer. This is another AWS tool that allows you to basically see how you are spending your money in the platform. And it's very useful to set up those alerts that I was mentioning and control the total cost. This is my own platform, right? My own device. Coast Explorer is here on the left-hand side. And you can see for a certain period of time, the last 6 months in this case, how are you doing in terms of spending? And this has a few nice reports and a few nice ways to operate with it. You can, for example, filter for a service. And here I can say, just show me Braket and apply those filters. And then you can say, okay, show me here, group this information rather than just the service itself, which I know already. Let's use usage type. And you can see that how more meaningful information is starting to be shown here. IonQ, Rigetti, you see how the different devices are specified there. I'm going to go and pick a very narrow time frame for the last few days. So let me say, for example, today is 27th. Well, I'm going to pick from Friday until today. Let's see what that shows. This is just one block per month, and then I can split this into daily operations. So I have an idea on how I've been spending my money in the last few days. See that here, April 22nd and April 23rd were more active. It was almost $200 per day. And here I can see that on April 23rd, for example, most of my work was in Rigetti, which is the purple one. However, in April 22nd, it was more related to IonQ work. So that allows you to see, if you have a big team, how your developers are doing with the platform, how much money you are spending. And obviously, this is not exclusive to Braket. I'm filtering here for the Braket service, but you can do this with any other service in AWS, right? And that's a very handy way to check your costs after it happens. And here you can set up alerts and stuff like that as well. Okay. The next thing we are going to do is to go to Braket again. And go to the notebooks. And I think this is the point where I'm going to introduce a pause or a break before we go into the hands-on lab, because this is the part where we are going to start to actually write our code. Let me go back to the slides to see that I didn't lose my track. Yeah, we are in the hands-on session. Oh, we do the break after the hands-on session, right? So I have half an hour from now. Is that correct? Yeah. Okay. Perfect. So we covered the device availability that you saw on those windows and how to see the status. You saw how the QPUs are located in different regions. We saw the architecture. We answered some questions about picking the right simulators. You are going to see the simulators in action now. And the next thing we are going to do now in our hands-on is to build those circuits and find the task and interpret the results. Okay. Perfect. That will be before the break. I will take these questions at this point, or if you want to do the break now, it's also fine. How are we feeling?
No standing questions.
Standing questions? Okay. So let's get our hands dirty then. You saw me here. Actually, before we do that, yeah, let's go ahead. You saw me here how I created a notebook earlier. I'm going to bring the actual event engine window so you see the same thing as I'm seeing. Let's see where am I? Here. The notebooks. You created a notebook. Remember that I call mine Juan. It's here and now it's in service. So you should all have a running notebook now. You can click on it. And the first thing you're going to see is this window, bracket examples. Please go ahead and click on it. You have a lot of examples here. And this is a platform for you to play as much as you want and execute anything you want in these notebooks and check your results for the next 3 days. It's really, really good way to get your hands dirty with the device. My mission here, sorry, not with the device, but with the platform. My mission here today is to get you excited, okay? So we're gonna run a few notebooks that are very basic, but are gonna give you that taste of, I want more, I like to see more advanced stuff or see what happens when I change this and that. That's exactly what I want to enable you to do, okay? In these folders, you have quantum annealing, penny lane that someone mentioned before, some examples for QML, for quantum machine learning. You have 2 folders for hybrid algorithms and some of the bracket features and advanced stuff like the Grover search algorithm and other things that are more evolved. We are going to get ahead with the getting started folder. And here I want you to go ahead and open the getting started notebook. This will open something that you already saw before when you saw my presentation. And to keep a little bit of the mystery, I'm going to ask you to please go here to kernel and click on restart and clear output. So that way you don't see the execution already. We keep a little bit of the mystery, as I said. Once you have executed this, you will see that there is only cells with no outputs at all and just a few lines of code. How do I interact with these devices? How do I do things? Okay, so first of all, I need to import a few libraries. The Amazon Braket SDK is based on Python. It's a familiar language. That's all you need to learn, a few libraries, that's all. What I'm doing is to import a few math libraries in order to represent my results. And the very first, very basic stuff that I do is to basically import a circuit and local simulator from these 2 SDK libraries. And then I can run this cell. To run the cell, you can just press Shift Enter or mayúsculas Enter, or just click on Run here. And that will show a number when it's finished when it has finished the execution, saying that it runs successfully. If it doesn't run successfully, you might get an error, and then you will troubleshoot it. Second one, we're going to build a circuit. This circuit is a bell pair. What is a bell pair? So we're going to build a circuit with 2 qubits, right? And those 2 qubits are going to be entangled together, and we are going to bring them to superposition of states. What does it mean? It means that those 2 particles are going to be in an indeterminate state while the computation is taking place, where we don't know if it's 1 or 0 yet. That's what is called the superposition state. While the computation is taking place, we are in this superposition where you have the same chances of obtaining a 1 than you have of obtaining a 0. So it will be a 50-50% chances to obtain each results. That's what we achieve when we use this H gate that you see here. This is the Hadamard gate. It's a quantum gate that brings my qubit to superposition of equal states. And then we are going to append the CNOT gate. The CNOT gate is the control NOT gate that is going to allow me to subject the result of the first qubit to whatever happens in the first qubit to the second qubit. I'm going to print it just to make it a bit more clear. You can go ahead and do the same. I define this circuit as bell. And when I execute this, you see that I have 2 qubits. My Hadamard gate is in the first qubit, and my control NOT gate is operating on the second qubit. That is called here Q1, right? The X gate is basically flipping the value of the qubit. If this is initialized as 0, the value of the qubit will turn into a 1 when I read it. However, in the control NOT gate, I am subjecting the result of this qubit to what happens on the first one. If you remember, I told you that the Hadamard gate brings the qubit to an equal superposition of states, so either 0 or 1. So what that means is that qubit 0 that initially gets initialized to 0 is going to end up being 0 or 1. 50% of the time is going to be 0, 50% of the times is going to be 1. Roughly speaking, this is all probabilities at the end of the day. The second qubit is going to say, okay, if the first qubit stays on 0, I will not change my state. I will also return a 0. However, if the first qubit changed its value to 1, I'm going to flip as well the value of the second qubit, and I will return a 1 as a result. What that means is that 50% of the times in this circuit, I'm going to get the value of 0, 0. 50% of the times I'm going to get the value of 1, 1. That's our circuit definition. And then you can attach here as many gates as you want, or append as many gates as you want after the circuit definition. Hadamard gate, control NOT gate. This is my control qubit, number 0, the first one, target qubit, second one. After I have defined my qubit and I have an idea on how it looks like, this is a very basic example, I can go ahead and submit the circuit to an actual device. We are going to start simple. We are going to start with the local simulator that I told you that is the one that comes by default, pre-installed with the SDK, and is totally free to use. So you can use this anytime by downloading the code from our GitHub repository. I'm going to store my results, and I'm going to specify how many times I want to run this circuit. So I use the device run parameter, and I say, or library, and I say, okay, the circuit name is one of the parameters, and the number of shots is the other parameter. In this case, I'm executing 1,000 shots. I could do 10,000, I could do 83, it really doesn't matter. What you need to remember is that this is a probabilistic result, right? So the more samples you get, the more significant the result will be. For this simple example, I could use just 100, and then I just change it to 100, so it runs a bit faster. And then what I'm doing is to count how many times my qubits have been 0, 0, and how many times they ended up being 1, 1. This is what you see here. 53 times this circuit turned out to be 0, 0, and 47 times it was a 1, 1. If someone in this audience runs this circuit and gets a 50-50, that would be the first time that I've seen it. Please let us know. If you ever run this and try to run it as many times as you want, you get a 50-50 split, you get my appreciation. Then we can use the matplotlib to actually print this in a more visual way, right? This is the number of results for each execution. And with this, we have run our first quantum experiment. We took 2 qubits conceptually. We bring them into superposition and then entangle them with each other. And we run it in an actual simulator. The next thing we can do is to actually start playing with the managed simulator, or more complex situations, or sending them to an actual QPU. That I bet is what you want to see today. To do that, to be able to actually run it in devices, I'm going to ask you to import a couple of libraries. The first one, as you can see, is the same. You can copy it from here. You see these two. The local simulator, you already have it, so you don't need it. You don't need to import it anymore. But now, besides the circuit that you see here, we are also import the gate and the observable. So please go ahead and type that. And in order to run in simulators and quantum computers, you will need to also import the device library. With those 2 libraries, you are able to execute your code in a quantum computer. After we have imported that, you can specify which device you want to run this into. The first simulator that we saw, if you remember, was the state vector simulator. So this is how it is defined. You just need to say device, or whatever variable makes sense to you, equals to AWS device. Just be careful with the notation, capitalization. Then how do you get this long string? You don't need to copy this from my screen. I can put it there in the chat, but the best way to obtain this number is, remember, going to the devices section. You might have another tab on your browser. So you can go to the simulators, click on SV1, and from there, you see device ARN. You just need to click on these 2 squares, and that will copy the name of this Amazon resource name and just paste it here. When you execute that cell, you are basically saying, now my new endpoint is not the local simulator anymore. Now it's a managed simulator. Then you can just copy the same code. You can basically grab everything from here. You see the device definition is here. You change the device, and you can just copy this and paste it below. Go ahead and do that. I'm going to do this. I just store my result, execute device run. The name of my circuit, it was Bell. And the number of shots, I'm going to put 1,000 this time. And then again, I'm counting the number of shots. You see that it's taking a little bit more time. This is a managed result, and I put a managed device and also put 1,000 shots, so it takes a little bit longer. One thing you can do after executing this task is to, well, once again, you can copy the code from above as before, just to plot it, and you see it in a graphical way, the same thing. But you can also go back here to the console and check tasks. And as you can see, you see your task that has been executed. And if you click on that link, you will be directed to the S3 console, the storage console, and you will be able to download the file and check the results by yourself. Feel free to go ahead and do that. I will do it with a later example as well myself. So you see the flow, right? I think you're starting to get an idea how simple this is. I create my circuit. I can make it as simple or as complex as I want. You have the documentation available to build more type of gates, more qubits, and play with different options. And you just need to define your endpoint and run your code and collect your results. Because this can be very complex, we store everything in a task. that it might take minutes, hours, of time to execute. So that's why we like to store the results in a file and have a status here that will tell you when it's completed. I'm going to do one more thing, that is going to be to use the Tensor Network Simulator. Before I do that, okay, let me get only part of this code. Let me do it like this. Let's use the Tensor Network Simulator, or TN1. So for that, you're going to have to use device equals to AWS device, and here you're going to enter the ARN, the Amazon resource name of your device. Please go ahead and do that. And at this point, you know how to do it. I'm going to give you a few seconds while I sip a bit of water. In the meantime, if there's any question hit, I can answer them.
Yes, perhaps the most important question. The usage of simulator and the device is straightforward, but could you explain the circuit itself and point us to how we can read more about building these circuits?
All right. Very good. The circuit itself. This is a proof of concept. It just is showing that you can bring two qubits to superposition and entanglement. So that is useful because when you are running an optimization problem that has many possibilities, that in a traditional computer would be a serial task to run, exploring the different possibilities, in a quantum computer, you are going to be able to reduce the time of that execution dramatically or run it much more effectively if you are able to map your problem in a circuit in the right way. So per se, this circuit is not resolving any real-life problem. And at the state that the current hardware is, you will not be able to do amazing things, let's say, change the world using a quantum computer today. However, the potential is there. If you think, for example, on factorization, that's probably a popular topic. When you are factorizing numbers, basically you are saying, this is a number, tell me the two prime numbers that when you multiply them, the product of those numbers gives me that number. So if I have 15 and I go for the factorization of 15, the computer will tell me a 3 and a 5, and that will be my result. A digital computer can definitely do that, but a digital computer is much better on doing the actual product. Just you provide a 3 and a 5 and it gives you a 15. When you are not talking about two numbers, a two-digit number, but you are talking about 600 plus digit number, which is RSA 2000 encryption, then the machine, a digital device, might take hundreds of years to give you the answer. However, these algorithms, the ones that you can find in the folder in the advanced algorithms in the folder that you saw before, will show you how in theory you could do factorization of prime numbers in a much more efficient way. And when you have a big enough device, you will be able to get the results and effectively break that encryption, right? That all internet today and all security today is based on the factorization of numbers. I'm not sure if I'm answering your question correctly, but the best way to start is to start exploring these circuits and see how they get more interesting in complexity as you go along. So you can get, for example, in the advanced ones, you have the Grover search algorithm. That is the one that I was mentioning earlier. Well, that's not the one, but this is one of the search algorithms that are more complex, and you will see that have more convoluted circuit definition. And the good thing about these circuits is that it comes with an explanation, theoretical explanation. Obviously, you will need to be familiar with the math that involves them, but then you will be able to write things like this that are able to solve real problems, right? You see a bunch of Hadamard gates here, the X gate that flips the qubit from 0 to 1 and the other way around, the Z gate that executes certain rotation on the qubit. And that's a very good way to start getting familiar with these things. The platform itself is meant to execute circuits, so it's not like an educational platform. If you need basics about what is a gate, how many gates are out there are other resources for that. We can provide some advice in our final notes when we send the follow-up with all the presentation. We can give you more resources and links with that you can read to get familiar with the gates. Hopefully that's good enough for as an answer and hit.
Yeah, that was good. Thank you. One question which has been answered, but for everybody else, I think this will still be helpful. I have tried TN1 simulator with 10,000 shots and I got an exception. Is there a limit in number of shots for that simulator?
There is. For the tensor network simulator, I believe is 1,000 shots, what you can execute. You cannot run 10,000. Also the number of qubits, which for this example shouldn't be a problem, but maximum 50 qubits. Try with 1,000, and I love that you guys are trying things, because that's what this is about. Any other question?
No, all good.
Thank you. Thank you very much. So as you can see here, I'm taking the tensor network simulator ARN, and I'm going back to my device, to my notebook. I define that. I'm going to do something a little bit bigger now. It's not much bigger. In fact, basically, I'm going to put together another CNOT gate in the next qubit, so turning effectively this circuit to what is called a GHZ circuit. It's a good benchmarking circuit because basically allows me to see what happens with I entangle many qubits with each other, right? I take a Hadamard gate in the first qubit and I can put as many qubits as I want or as big as the device is in my subsequent wires until I occupy the entire space. So I invite you to write your own function to set up a lot of CNOT gates here up to the limit of the device that you're going to be using, right? You already saw some of the limits that you have. For tensor network simulator, in this case, it will be 50 qubits. So you could place 50 lines over here and that will run. It will take longer, but it will run. And then for the Rigetti device that you saw earlier, we'll have 80 qubits. You could create an 80 qubit circuit and run it in the device, and that's going to work as well. So I invite you to do it. All right, I'm going to just copy the same thing that we had in previous cells, just everything in one group because we are familiar with it now. The result, the name of my circuit, the number of shots, I'm counting results, and I'm printing it in beautiful format. This is running now. As you can see, it takes a little bit longer, and I can also go here, check my tasks, and you see that the second task is completed. All right, so from here, what we are going to do is to move on to the next folder. We were in getting started. Feel free to keep it open if you want and add the code to that notebook, or go to number 2 and running quantum circuits on QPU devices. Let's do the same thing again. Go to the kernel and restart and clear your output. So that way we start with a clean slate. All right. So as you can see, nothing is different here. I'm importing my same math libraries, and I'm importing my bracket libraries. As you can see, the ability to run circuits, to execute gates, to send instructions to the device. This is the local simulator. This is where all the devices, the rest of the devices are, and this is going to allow me to create tasks in an actual quantum computer. With those libraries, this next cell is basically telling you which gates are available and which gates are supported. This is important, answering one of the previous questions that I got. because when you are writing very complex circuits, you might find differences between Rigetti, IonQ, and Oxford quantum circuits, the three gate-based devices that we have today. So with this command, you will be able to see all the list of gates that are common to all these devices, and that way you can write your circuit and change endpoint in a very convenient way. I'm gonna run it. You will see there like things like our SDK, first of all, for all the simulators. You see things like the CNOT gate, for example, here that is common to the Rigetti device and also common to the IonQ device, and also the OQC device or Lucy. So some gates are basic, right? Like the XYZ rotations and things like that. They are basic gates and they will be available in all of them. And by the way, if you are picking a gate that is initially more convoluted and is not present in every device, every gate can always be decomposed in XYZ rotations. So you could potentially decompose any gate to a simple version that execute in every single device if you wanted to. We are preparing the same Bell state. This is a more beautiful representation with the mathematical logic behind it that explains the superposition of these two states. Okay? If you are interested in linear algebra, go for it, go nuts. It's a very interesting field. Here you see that we are defining the circuit again. You don't need to say control equals and target equals. The system knows already that the first parameter is the control qubit and the second one is the target qubit. So you can execute it as it is. I'm printing it, and here I'm not doing anything differently in the next few cells. As you can see, it's the same local simulator that you did before. Now, here's where the interesting part comes, and probably what many people were waiting up until this point. We are going to execute this same code in an actual device, and to do that, I'm grabbing the ARN of the Rigetti device. This is 80 qubits. So I invite you, if you want, to make this circuit more complex and add a few gates. Feel free to explore based on what you have in this cell, the different gates available to you. And if you want to play with it and add additional complexity, go ahead and do it and append more gates to this circuit. I'm taking different values other than the counters here. We are not going to go into details of that today, but it's available to you there to see that you have other options. And then I'm going to run 1,000 shots in the Rigetti device. This is running in asynchronous mode, and that's the reason why I wanted to run it in a new cell, because there is additional logic. I'm grabbing the task ID and also the task state that are properties of one of the properties in the Braket SDK. That way I can see that this is now in a status created and I don't have to wait for it to finish. Why are we doing that? Because as you can see, you saw before that there is availability windows. If this device is offline right now, I don't want to hang on this cell until my code runs. I want to keep executing other code or maybe do other things. So I just want it to return the status of the task. And with this next cell, I can basically say all the time what my status is. This went from created to queued and finally to completed. So this is your first real quantum computer results that you can go ahead and check. Okay, so this device is available in US West 1, if I'm not mistaken. Yeah, Rigetti is, you can see, US West 1. So you might see a blank window here because of the event engine limitations. Let me check that. Sometimes works, sometimes doesn't. Go to tasks when I change region. No, it's here. Let me know if you cannot see this screen, but what I did basically was to change from Northern Virginia or US East 1 to Northern California or US West 1. That takes me to the main devices page and then just move to tasks. And that will show me my Rigetti task that has been completed. I can click on that link. And as you can see, it tells me when it was created, when it was ended, and also where the results were stored. There is a new file here called results.json that I can basically open and check my results. Download it and open it. This is the detail of my experiment. You see, for every shot is represented here. So there will be 100 lines or 1,000 lines, depending on the number of times that I executed this circuit, with the result for each single shot. And if I go to the very bottom, I will be able to see more details. It took 2 seconds to execute. These are the fidelity gates of the gates that I executed. And this is the qubit rewiring, which is very interesting as well. Meaning that this is how the device was reorganized. If you remember the topology with the several rings connected to each other, qubits 37 and 30 were picked first. And this is something that the machine randomly picks for us. If you activate a special mode called verbatim, and you will be able to decide which qubits specifically you want to use in your circuit. So you will be able to come here to bracket and say, okay, for the Rigetti device, I want you to pick qubit number 1 or number 2, or qubit number 13, or qubit number 100. It depends, right? So I'll come here. And you might be able to see in this calibration window, which are the top best windows, and pick only qubit 11 and 26, for example. That's not something that is activated by default, but it's an option when you are running more advanced examples. And this is what you see here, the calibration. Okay, so that's your results. Let's continue, because we only have 5 minutes left before we finish this hands-on part. And I'm going to ask you to keep exploring, keep executing these cells. We are going to do exactly the same thing with IonQ, the other device that you saw earlier that is based on trapped ion technology. We are reading ones and zeros as well. We are also using the properties or superposition and entanglement, same quantum properties, but the hardware implementation is different. This time we are dealing with an ion that is being controlled by laser tweezers. It's not science fiction, it's real. This is pretty cool. As you can see, the task has gone from created to queued. It's not completed. What does it mean? What's going on? Well, what it means is that if we go to devices and check on IonQ, that is in USTS1, and we go to the right region. I am in the right region already, USTS1, and I go to my tasks. I will see that my task is in queued state. The device is available right now. The device is in the execution window. However, at this moment, for whatever reason, there might be a lot of people maybe using the machine. This is not like digital computers, right? That we have clusters of machines in the cloud working so they can respond immediately. There's one device available for everyone. So your task is queued, and in the next few minutes, it will be processed, and this will move from queued to completed. And at that point, you will be able to see the results of your experiment. But the cool thing about this is that basically, as you can see, you can write your code, change your endpoint, and execute your same experiment without changing a single line, without having to learn the documentation from IonQ, from D-Wave, from Rigetti, from OQC, with just one programming language, how to access to a variety of devices. And the count is on and on. There are more coming, and they will all be using the Braket SDK. Okay. We can do the same with Oxford Quantum Circuits. That one is not going to be available until the next 17 hours. So definitely you will not see the result of this one today. But when the execution window starts, sometime tomorrow morning or late night in Europe, but that goes into create status. And again, I challenge you to find where Lucy is, go to the right region and check the task and see that the task is there, okay? It doesn't mean that you're going to use the notebook in the same way that we did before to see your results. If we do execute this piece of code for Rigetti, what we are saying is basically, okay, tell me when the task is completed using the device properties, and then just load the result using this function. and other information like the metadata, the number of shows, the device name, and all that stuff, and print it in beautiful format as we did before. If it's not, just return an error saying, sorry, your task hasn't completed. In this case, it's completed, so I'm just printing a little bit more information. I put it here just for you to see as an example that it's not only about counting qubits, you can do more stuff, and the documentation is there for you. And look at this. This is very interesting, right? We have 4 bars now. There's no 0, 0 and 1, 1 anymore. So this is the noise of the devices that I was mentioning earlier. These devices are not perfect, still have errors, and you have to account for these errors. And this is one of the reasons why you should run many shots in a device, because you have to take a probabilistic distribution of everything to know if your result is reliable. If you run only one time, you will not be able to know or to differentiate the noise from the signal, right? You see here 0, 0 and 1, 1, which is the majority of it. But you see also 1, 0 and 0, 1, which are results that are not correct. They are not expected, but you have to account for them. This is a real computer giving you real results. You can compare this graph with the other ones when they finish the execution. IonQ is queued right now. Lucy is right now in created status. If you run these cells, tomorrow you will be able, if you access in the morning before the workshop, you will be able to see how the task finished, and you will be able to check your results and see how differ from each other, right? And so if I run this code for IonQ, it's exactly the same code, just telling me that my task is queued and I have to wait for it. Okay. And then this is just another piece of code. You can, I'm not going to run this, but basically this is the polling state, which you are constantly querying your device every few seconds for a state, for a status, and you get your results when the task is completed. And that's another way to do it. This is just purely Python logic built on top of the Amazco Braket SDK. So I challenge you to build more complex circuits, to play with the gates, to see what you get. And if you want, you have 3 full days included today to go to other Amazco Braket examples, go to the annealing part, for example, and see how D-Wave works in action. You see here some interesting notebooks about the device anatomy and other optimization problems. And bring your questions tomorrow. We will be more than happy to answer anything we can. That's all I have for you today. As for the hands-on session.
We have half an hour more, isn't that correct?
Oh, we do. That's true. Well, it seems like we are a little bit ahead. I really need to take that 5-minute break, but after that I can come back and I can get more questions, if that's okay for everyone. Right, so let me do one thing. See a blank screen right now?
Yeah, only see a blank screen.
Okay, I don't know what is that. Let me see. I see someone is raising hand. I don't think I have the ability to unmute you. Let me see. Is it okay to type the question instead? And if you want to do it in Spanish, it's also fine. I can read it in Spanish and give the answer in English, whatever you feel more comfortable with it. Because I know that the majority of our audience today are Spanish speakers. I hope I spoke slow enough for everyone to follow. I'm just trying to get out of this screen, sorry. There you go. So this is, I think it's 6 p.m. in Spain. It's 4 p.m. UTC. That is the time that we are using for everyone as a reference. We're going to stop here for 7 minutes. And after this break, we'll come back. I will answer questions, and then Nihit will take over to continue with the second part of this workshop, where you will be able to connect the Amazon Braket platform to the QuantumPath platform, a quantum platform called QuantumPath, in order for you to make all this process of writing circuits even simpler than what you have seen here with Amazon Braket. Let's take that break, and I'll see you in 6 minutes from now. So you can see me. Start video. There we go. Yeah, I just was pasting a few messages there in the window. I'll give 1 more minute to people to come back. I'd like you to start filling that survey if you don't mind. The event hasn't finished. This is the most exciting part, probably what is coming now, where you will be able to see how you do not need to actually type code if you are not an expert in Python, or you don't want to learn every single library that Amazon Braket uses to access these devices. This is why our partnership with Quantum is so powerful, because they add an abstraction layer on top of our platform that allows you to, in a very intuitive way, have access to these devices and build your circuits. And I think you're going to love the second part. Okay. So again, please use the survey and give us feedback. We really appreciate that. If you do it, it makes our day when we get not only good comments, but also ideas to improve on things that were too slow, too fast, too difficult, too easy. Okay? I'm going to give now the word to Nihit, that has to talk to you about how to create the QuantumPath solutions, and it's going to help you to configure the actual quantum environment. We'll go in the background and we'll be helping with questions if there is any. I think there was some question earlier before. Maybe before we do that, Nihit, I can answer any other question that might be remaining from the previous session. What do you think?
Yeah, we have time for questions for sure.
Go for it.
Vanessa actually answered a lot of questions here on the chat.
Vanessa is awesome. Thank you, Vanessa.
One question. Can we make pulse level control in superconducting qubits with Braket?
We cannot today. It's one of the most requested features from our customers, and I can tell you that there is an effort ongoing to support that in the future. But today, you don't have pulse control for superconducting, no.
Right, another one. What is your opinion about silicon to build quantum chips?
It's another horse in the race, right? It seems like a very natural combination because silicon is abundant and is already very well known on how to model it. But the thing is, we don't know, there's many parameters, right? The readability speed, the fidelity of the gates, the number of errors that the qubits produce, and how scalable the devices are. There are great ideas out there, and probably silicon is one of them, where qubits at a lower scale connect really well. But it's a matter of scalability as well, and making big devices that they can resolve real life problems sometime in the future, hopefully. I don't have an opinion about this. We don't have a formal stand. The AWS and Amazon Braket formal position on this is that we want to democratize the access to quantum computers. If tomorrow there is an option for silicon that is easily accessible from the cloud, and we talk to a partner that is building those, and we can make it available in the platform, definitely we'll put every effort to put it there for customers. But it's just another player.
Okay, and one more question. Are there alternative ways to define circuits apart from using the factory pattern? I mean, applying more gates line by line with some operations or so. I'm just asking or thinking in code maintainability and possibility of building circuits dynamically.
Definitely. You can do that. You have the basic SYZ rotations and other basic gates like the X gate, C not gate, and you can decompose any circuit into these basic gates. Nothing stops you to dynamically create a circuit. And even more, you could even change the circuit dynamically with every shot. So you could create a task, and that's something that a few investigation groups are doing, research groups are doing. You run your first shot, and in the last part of the circuit actually change a few gates, and in the next shot you give it a different type of gate and see the differences. In terms of Amazon Braket, that will mean that you create a lot of tasks with just one shot in each task. So you have to mind the pricing on that model. And that's the only advice or word of caution that I will give you on that. If you change dynamically on the execution of your circuit itself, just mind the number of tasks and shots that you are going to produce. With the first notebook that I executed that I'm going to share with you, you will be able to easily see what the pricing is going to be. I see a lot of questions here. Let me see. Why we're using superconducting? I don't have a good answer for that. Our investigators believe that it's a good path. I know that we are open to everything, but definitely we decided to go into that direction for our efforts to superconducting. We acknowledge the fact that there are other technologies that are good and that are right now out there, but we decided to progress more into superconducting. Not that we believe that there's one better than the other. Nobody can tell you today which one is better, but that was our choice. Right, photonics is true that it runs better in room temperature. That is totally true. There are other disadvantages of photonics with respect to trap ions or superconducting, and at the same time room temperature allows to reduce things as well and potentially do things in a much more smaller size, which is a good thing about photonics, right? But yeah, it's just another option. Density matrix approach. I would love to touch on that because it's one of my favorite topics. If you go to the folder in the Amazon Braket repository structure that says Braket features, you will find a whole notebook on how to create noisy circuits. With the DM1 simulator, the density matrix simulator, you can create your own noise channels and your own density matrix custom matrices where you can create your own noise channels. You have a few predefined ones. For example, you are able to simulate bit flips, phase damping, and you can define those and circuit readout. So at the very end for the whole circuit, you can do it as well in circuit initialization. So before you start running your circuit, you can set up all your noise, which is another real life situation that happens with these devices. And then within the execution of the circuit itself, you are able as well to define noise for one single gate. So if I have the X gate, define that all the appearances of X gate will add 10% of bit flip noise, for example, or per qubit. You will say qubit 3, 4, and 5 are clean, but my qubits 1, 2, and 7 are going to get noise 20% of the time, or depending on other variables. I encourage you to take a look to that that notebook. And tomorrow morning we can start, or your afternoon, depending on where you are in the world. At the beginning of the next session, if you want, we can start with a few Q&A, and if you run these things on your own time, we can try to answer your questions as well. All right, well, I see differences on opinions, which are all respectable. This is the beauty about this field, right? That this is a lot of components. There might be things also that I ignore, and other people are getting deeper into it and know more than me. So this is why this is a rich discussion. Our approach is to try to provide access to everyone, as many computers as possible, so everyone can try different options. Okay. I think we can continue, unless there is any other question that you guys had there that I only see the last few in the chat. So let me know if you want me to answer any other that you might have there.
All right. I'll take over then, Juan.
Perfect. Thank you, Nihit.
Okay. Do you see my screen in?
We see the yeah, that's perfect.
All right. Okay. Okay, so now we'll move on to connecting Amazon Braket and QuantumPath. But before we do that, I wanted to quickly summarize what Juan just said, right? So in essence, this architecture diagram that you see in the screen right now is what Juan discussed. As an user, all of you can use Amazon Braket through Amazon Braket Console by using our managed notebooks directly. Or if you wanted, you could also use local IDE and use Amazon Braket through any local IDE of your choice. And what we then do is provide you the option of managed simulators. As you saw, we have a couple of those, as well as some quantum hardware. Those are not built within Amazon Web Services. So these are all our partners that provide different quantum hardware, and here's 4 for now, and QEra is coming soon. You also saw that Amazon Braket is like any other AWS service in that it is well integrated with other Amazon services like CloudWatch. You also saw Budget, and we also played a little bit with IAM, right? So we used IAM to create users who had different permissions from the initial user we have. And also we played a little bit with S3. S3 is the bucket where your results are stored. So reiterating what Juan said a couple of times before, our idea is to make quantum computing a cloud service. So this will continue to integrate with more quantum services as time continues, as well as we'll bring in more quantum hardware as they become available to the market. So based on the information that we shared with you earlier today, really at this point, you're now ready to go and play with quantum computers. So to do so, AWS free tier comes with 1 hour of free simulation time. You really can just go ahead and log in on the free tier AWS console and get going. Or if you wanted more resources, we also have something called a research credit for quantum testing and experimentation. So especially as academic users, we highly encourage you to apply to this program. I'll paste a link to the program in a little bit. But researchers in universities do get access to research credits to do much more than what our free tier AWS lets you do. Okay. All right. So now at this point, I'll switch gears a little bit and talk about QuantumPath, which is Quantum's proprietary software as a SaaS solution. Right? So we did see that Amazon Braket is actually quite self-sufficient, but if you wanted a more simplified platform and many other enhanced capabilities, QuantumPath is the way to go. And that is because QuantumPath, which comes from Quantum, adds to what Amazon Braket can do for you. For example, You get notified as to what is going on within the platform. You also have access to additional simulators that are not available through Amazon Braket. So Quantum also provides in-house simulators. And to add to those capabilities, there is really a complete, sorry, I'll go back to my screen. Can you see my screen all right?
Yes, we see it.
Okay, all right, back to where we were. All right, so what was I saying? Okay, so yeah, Quantum's QuantumPath adds to much more than what Amazon Braket allows you to do. It provides a complete pipeline for you to create industry-ready quantum software solution. Using QuantumPath, you can create circuit definition as well as Kubo formulation through a very exciting and intuitive code-free interactive platform. You'll see tomorrow, Pepe will do a demonstration where you can see how you can drag and drop circuits and build your quantum code. So that is quite exciting to me. And as an end user, QuantumPath keeps you in the loop by providing notifications throughout the process, really lowering the bar and the barrier to entry for non-quantum experts. You also do not have to worry about the cost. QuantumPath ensures that you're paying the least possible cost to run your quantum code and run different quantum hardware available through Amazon Braket. All right. So QuantumPath really takes it a step further. If you're new to quantum computing, you can annealing optimization problem using QuantumPath. If you wanted to evaluate gates, you could also do so without really having to worry about, procuring licenses, cost, infrastructure, or even machine downtime. Truly, you have quantum computing on demand, and you only pay for what you use. Your data is protected following AWS best practices. Quantum also takes care of strict control policies over your circuits. So you have control over the access of your quantum circuits, and all of that follows AWS best practice. And QuantumPath will continue to evolve as customers ask for more features as Amazon Braket evolves as well. Okay, so with that information, now we will go ahead and set up the hands-on session of the workshop where we will connect Amazon Braket and QuantumPath together. So to do so, let me get out of the presentation mode and bring my browser, and I encourage you all to do so. So if you can bring up a browser, that'll be awesome. All right. Okay, I'm starting with a fresh browser here. So the first thing I'd like for you to do is go to this box. Where is my chat? Okay, chat's here. Okay. All right. On the chat, I have pasted the link to QuantumPath. Please go ahead and click on the link. Right, you should be here. So once you get here, this is the link to QuantumPath. Now let's go ahead and sign in. Username, anything is okay. I'd just say need demo, AWS, provide an email address, set up a password, and then repeat the password. And that is all. And now we'll go ahead and complete the enrollment. Okay, once you've completed the enrollment, you should see this page. Now, go ahead and click Go to Login page. And I will. Access denied. Okay, let me go ahead and do that again. Okay, should work. And then I will accept the end user agreement. I hope you guys could get there. I see the chat that it worked for someone. Okay, please confirm that it works for you. Perfect. Okay, I see a couple of working. All right, so once we're there, what we'll do is now go to Tools. On the Tools, you will also see Quantum Solution Catalog. Click on the Quantum Solution Catalog, and then we will go ahead and create a new solution. Click Create a New Solution. We'll again call this, it doesn't matter what you call it. I'll continue to call it needp.aws. Dot doesn't take, okay, we'll just see needp AWS, and for description, I'll see needs QPath demo. Okay. And then we'll go ahead and save this. Once you save this, on the right side of the Save button, you see Platform. Click on the platform. And so up here, you will see Amazon Braket. Click Amazon Braket. Okay. And this is a pretty important step. So when you click Amazon Braket, tomorrow in the demo, we'll be using TN1, Rigetti, and IonQ. So we'll pick those three devices and initialize those three devices. All right, so let's go ahead and do that. First, I am clicking Rigetti Aspen 1. I'll maybe type that in here as well. Please go ahead and click on Rigetti Aspen 1. And so after you do that, on the right-hand side, you'll see this Edit button, okay? Please let me know if you want me to speed up or slow down. I'm going as slow as I can. Once I click Edit, there'll be a pop-up for user, password, and token. So this user is the AWS access key that Juan asked you to save in the beginning of this workshop. It should look something like, I'm copying my access key. So the user, again, is your access key ID. And so the password is the secret key that you had downloaded again. So please go ahead and bring your secret access key and put in the password section. I'll repeat myself once again. User is the access key ID, and then the password is the secret access key. And so for the token is the region you'll be in. So US East 1. the way you write it is US East 1, and then we'll pipe this with the name of your S3 bucket, right? So remember the name of this S3 bucket that we enabled that we were provided when we enabled Amazon Braket. So now let us go ahead and bring the name of the S3 bucket here. All right, once we have that, we'll go ahead and update this, and that should be it. So what it does is now connect QuantumPath to the AWS account that each of you have, right? So we did that for Braket Aspen 1. Now we'll go ahead and do the same thing for IonQ, right? Let's go ahead and repeat the same exact thing for IonQ. Edit for user is the access key. And for password is the secret access key. And the token is US East 1, which is the region we're in, and the name of the S3 bucket. In my case, this looks like Amazon Braket and some bunch of numbers. How do you get the user credentials and token? Yeah, so this was the information that you had downloaded or taken a note of in the very beginning when you created IM user with Juan. And if you did not do so then, unfortunately, you'll have to go ahead and create a user again. Okay. All right, now we'll go ahead and update this. This is for IonQ. And one more time, we'll do the same thing for TN1. Right, so user, I'll go ahead and copy my access key, and then the secret access, and US East 1, pipe it with the bucket name. So the bucket name is the name of the bucket that you were given when you initialized Amazon Braket. Okay, all right, now we'll go ahead and update it. And that is really all you have to do to create a connection between QuantumPath and Amazon Braket. And tomorrow, when you come in, you'll be ready to go and we will jump right in on QuantumPath. Okay, now let me go ahead and go back to my presentation again. And if any of you are still following me, here's a summary of what we did. So we went to QuantumPath, then under Tools, we created Quantum Solution, and then we enabled IonQ, Braket, and TN1 using your AWS access key, AWS secret key, and the region along with the S3 bucket. All right, that is all that you need for the connection. Now we'll move on to the next step. Was everybody able to follow? Let me quickly see the chat. Okay. Right, awesome. So while we do that, a reminder again to fill out the survey that Juan pasted on the chat earlier. And if you have any questions, please feel free to follow up with either me or Juan, particularly about Amazon Braket. Here is our email addresses. We will try our best to answer your question as soon as we can. And that is it for the day. If you now have any questions, I'll stop sharing my screen and we can take questions. Juan, if you'd like to come online, please do so.
Yeah, those are the devices that we are using, Rigetti, Lucy, and TN1 initially.
Oh, okay. So my bad. I did say Rigetti, IonQ, and TN1.
Instead of Lucy, it should be IonQ, the one that we set up. It's just because the availability windows are better. And so we can see more things that way.
Okay. All right. Any question?
Sorry, go ahead. The floor is yours.
No, I was going to say at this point, we also have Pepe with us. So Pepe will be able to answer any questions related to QuantumPath as well.
We can send you the instructions in PDF. That's not a problem. We can put that together. I think I have them for the AWS part. We can do it with the QuantumPath as well. Yeah, so let me see a few questions here. The PDF. Right, it's the region of the QPU. So you in the AWS console, you see that every QPU gets attached to a region. That's what you set up there. Yeah. We will be sending the materials, yes. We'll do it at the very end of the event. You just need to fill the survey that it will be on the second day and you will get all the materials. Yeah, we will be sending everything. Thanks for the comment, Fidel, on password strength. That's a good feedback. We will take note of it. And the QPUs available, or the ones that you are going to select, are Rigetti, IonQ, and TN1 was the third one?
Right.
TN1, the Tensor Network. That's correct.
And one question, to find the information about your S3 bucket, you can also go back to the console. Let me try and share the screen again. Just a minute. Right, so if you go here, you can, this is your AWS console, and feel free to go through S3. When you go to S3, you should see the name of the bucket that you have created, in case you did not take a note earlier.
Jose, we are always hiring. That's the page to the main quantum computing web page in AWS for hiring and recruitment. There are always undergraduate programs for students. I'm not intimately familiar with those, but I'm pretty sure that if you give a look to that page, and you will be able to find some undergrad programs. Also, if you want, feel free to drop me an email. I'm pasting my email address there, and I can put you in touch with someone to get more information about undergraduate programs. Yeah, tomorrow we are going to be covering the whole platform, QuantumPath, so it's going to be an awesome day. All right. Well, Mihit, I think it's time to wrap up. I'll let you finish the show.
Okay, all right. Last reminder, if you have not, please fill out the survey. We really appreciate the feedback. We want you to tell us what we did right, as well as tell us what didn't go right. And when you come in tomorrow, let me give you a sneak peek of what is coming up. Here's the agenda for tomorrow. So tomorrow, when you come in, we will quickly summarize day one and jump onto QuantumPath. So our goal tomorrow is to forget about Amazon Braket and think about how easy is it to run your quantum algorithm on quantum hardware directly through QuantumPath. With that, if you have any questions, we'll still take questions. If not, thank you for coming. We hope you learned how Amazon Braket works and how we're trying to democratize quantum computing today. Thank you.
Thank you very much, Nishit. Juan, you are
Thank you.
awesome.
You take care.